Before their thunderous steps shook the ground, before the T-Rex roared or the Stegosaurus grazed, our planet was already ancient, scarred by cataclysm, sculpted by fire, and teeming with life so alien, it would feel more at home on another planet than our own. For over 4 billion years, Earth has been rewriting its own story, and the age of dinosaurs was just one wild chapter in an epic saga. So what came before them? We're talking about a world where continents were constantly crashing and pulling apart. Oceans vanished and returned. The skies rained acid, and microscopic life forms waged evolutionary warfare for billions of years. Giant bugs ruled the air. Fish walked. Supercontinents broke like puzzle pieces. And yet, almost no one talks about it. It's time to change that. This is the untold story of pre-dinosaur Earth, a time of monsters without names, mass extinctions without survivors, and forgotten worlds buried deep beneath your feet. Are you ready to remember what history forgot? 4.6 billion years ago, there was no Earth. No blue oceans. No green forests. No sound. Just a swirling chaos of gas, dust, and cosmic debris spinning around a young, fiery sun. Then, boom. Not the kind of boom you'd hear in an action movie. This was the soundless violence of creation itself. Gravity pulled matter together, compressing it tighter and tighter, until a newborn planet ignited in a hellish birth. Earth had arrived, but it looked nothing like the world you know. For millions of years, Earth was a molten sphere of fire and fury. The surface was oceans of lava. Volcanoes erupted constantly. Asteroids, still left over from the solar system's formation, pelted the planet in a relentless bombardment. Imagine living inside an explosion that lasts 100 million years. No atmosphere, no water, no life. So how did we get from that fiery wasteland to you, sitting here, breathing oxygen and watching a documentary? Let's rewind this ancient film strip, frame by frame, and witness the forgotten prologue to everything. In the beginning, there was dust. Our story starts not on Earth, but before Earth. Roughly 4.6 billion years ago, a nearby star exploded in a supernova, seeding a vast cloud of gas and cosmic dust with heavy elements. This cloud, called a solar nebula, began to collapse under its own gravity. In the center, the pressure ignited a new star, our Sun. But around that star, a disk of leftover matter began to clump together. Pebbles collided and stuck. Pebbles became rocks. Rocks became planetesimals, mini planets the size of mountains or even Mars. Eventually, one of those grew large enough to become Earth. But Earth wasn't alone. Gaia, the impact that made the moon. Sometime in Earth's first 100 million years, a Mars-sized body, nicknamed Gaia, slammed into our young planet. The collision was so massive it vaporized part of Earth's crust and sent molten debris hurtling into orbit. What happened next was miraculous. That debris slowly coalesced into a glowing sphere that cooled and hardened over time. The moon. So yes, the moon was born from violence. And it's been with us ever since, shaping tides, stabilizing Earth's tilt, and maybe even protecting us from future impacts. But after the Earth was left shaken. Its crust was shattered. Its interior churned with molten fury. Still, something new was beginning to emerge. Water from the sky, water from within. One of Earth's most mysterious features is also its most essential. Water. Where did it come from? Some scientists believe water was trapped in minerals deep within the Earth's mantle and released through countless volcanic eruptions. Others think icy comets delivered it, like frozen messengers from the outer solar system. In truth, it might have been both. But the rain didn't start gently. Imagine an Earth covered in black rock, cracked and steaming from volcanic vents, and then sheets of rain pouring from the sky for thousands of years. Not a drizzle, a deluge. The first oceans weren't filled. They were forged by an endless planetary downpour. Lava met water. Steam hissed into the air. And slowly, the surface began to cool. From hellscape to waterworld, Earth was transforming. The Hadean Earth. Living through hell. The first eon of Earth's history is called the Hadean. From Hades, the Greek god of the underworld. Fitting, right? It lasted from Earth's formation up until about 4 billion years ago. And during that time, Earth was a hostile place. Temperatures soared. Volcanoes reshaped continents before they were even continents. Giant impacts could sterilize the surface in an instant. And yet, in the shadows of this chaos, something incredible may have been brewing. Life. At least the earliest ingredients of it. Life's first spark? We don't know exactly when life began, but the oldest possible chemical signs suggest it might have emerged as early as 4.1 billion years ago, while Earth was still recovering from its brutal birth. How? One theory points to hydrothermal vents, deep-sea fissures where superheated water rich in minerals pours from beneath the seafloor. Even today, life thrives around these vents without sunlight, feeding off chemical energy. Could these underwater crucibles have been life's original kitchen? Or maybe it happened in shallow tide pools, where wet-dry cycles sparked the first chains of self-replicating molecules. Or even in clay. Yes, ordinary clay, where amino acids could stick and organize themselves into the earliest building blocks of life. We may never know exactly how or where it began. But the fact remains, life did begin. And that changed everything. Zircons. Time capsules from the deep past. There's one more clue that tells us about Earth's earliest days. Zircon crystals. These tiny, nearly indestructible minerals are some of the oldest materials on the planet, dating back over 4.3 billion years. Trapped inside them are chemical fingerprints that hint at liquid water and even a stable crust, far earlier than once believed. That means Earth may have become habitable astonishingly quickly, less than 200 million years after its violent formation. Imagine that. A planet born in fire, already cooling off, settling down, and preparing to host life, while the rest of the solar system was still in chaos. The formation of the crust and continents. At some point, as Earth cooled, its surface began to harden. A solid crust formed. But this was no single, unbroken shell. It was fractured into massive, shifting plates floating on a sea of molten rock. Welcome to the birth of plate tectonics, a force that would shape everything to come. Mountains rose. Ocean basins formed. The first chunks of land, tiny proto-continents, began to float atop the denser oceanic plates. And beneath it all, Earth's iron core had already formed, generating a magnetic field that protected the surface from deadly solar radiation. All the pieces were in place. Earth had a crust, water, atmosphere, magnetic shield, and, maybe, primitive life. The planet was no longer just a ball of rock and lava. It was alive with potential. A world unlike any today. If you could stand on Earth 4 billion years ago, you wouldn't recognize it. The sky may have been orange or green from volcanic gases. The seas were acidic. The land, barren and black. Lightning crackled overhead. Meteor showers were common. But even in this alien world, life may have already taken hold. Deep in the oceans, clinging to rocks, copying itself quietly in the darkness. These were the ancestors of all living things. No lungs, no eyes, no bones. Just chemistry turned biology in the most miraculous way. From here, life would face incredible challenges. Planetary freezes, toxic air, deadly competition. It would be nearly wiped out more than once. But it had begun. And once life starts, it doesn't give up easily. Coming up next. So now we've met a young Earth. Hot, chaotic, and just barely beginning to cool. Oceans have formed. The crust is in motion, and primitive life might already be stirring. But this early world is still alien. Still toxic. Still shaped more by fire and impact than by biology. In the next chapter, we enter the Archean Aeon, a time when microscopic life ruled. Volcanoes dominated the horizon, and Earth's atmosphere was anything but breathable. And yet, these unseen microbes would slowly transform the world forever. Close your eyes and imagine Earth. Not the blue marble we know today, but a version so foreign, it would look like another planet entirely. A thick haze cloaks the sky. The sun, dimmer than now, struggles to shine through a suffocating orange-brown atmosphere. There are no trees, no grass, no animals, just an endless ocean. And above it, a sky that smells like rotten eggs. This was the Archean Earth, spanning from about 4 billion to 2.5 billion years ago. It was loud, it was dangerous, and it was alive. Not alive the way we usually think. There were no whales breaching the ocean, no flocks of birds, no dinosaurs, not even a single blade of grass. But deep in the scalding oceans, something extraordinary was unfolding. Life was fighting for its future, one microscopic cell at a time. Volcanoes, poisoned skies, and no oxygen. Let's start with the obvious. The Archean Earth was inhospitable. Think volcanic eruptions constantly. Magma oozed from cracks in the crust. Entire island chains formed overnight. Sulfur and methane belched into the atmosphere. The smell, horrific. And that atmosphere, well, it lacked one key ingredient: oxygen. Instead, the air was dominated by methane, carbon dioxide, and ammonia, greenhouse gases that kept Earth warm despite a weaker sun. That's right, the sun was only about 70% as bright back then. Without those gases, Earth would have frozen over permanently. But here's the paradox. Without oxygen, most modern life wouldn't survive. Yet somehow, life not only appeared, it flourished. So what was living in this toxic soup? The first microbial empires. The stars of the Archean were prokaryotes, simple, single-celled organisms without a nucleus. You can think of them as biological pioneers, eking out an existence in conditions that would kill us instantly. Some were anaerobic bacteria, thriving in environments with no oxygen, actually poisoned by it. Others were thermophiles, living happily in boiling water near undersea hydrothermal vents. Some ate sulfur. Others ate iron. Life, it seemed, would consume whatever chemistry the Earth threw at it. And then came a game-changer: cyanobacteria. These tiny organisms were different. They used sunlight to create energy. But unlike anything before, their process released oxygen as a byproduct. Photosynthesis had entered the chat. Stromatolites, time capsules of early life. If you ever visit Shark Bay in Western Australia, you'll find something that looks underwhelming. Just clumps of rock, clustered in shallow water. They don't move. They don't glow. They just sit there. But these are stromatolites, layered structures built by cyanobacteria, and they're alive. In the Archean, these mats of microbes formed colonies that layered over themselves generation after generation. As they photosynthesized, they trapped sediment and built towers of life, some still visible today, fossilized in ancient rock. Stromatolites are Earth's oldest known evidence of organized colony-based life. They're not just relics. They're survivors. And they tell a critical story. By 3.5 billion years ago, life wasn't just present. It was thriving. Why Archean life mattered so much. It's easy to overlook microbes. They're tiny. They don't roar or leap or sting. But the bacteria of the Archean eon accomplished something colossal. They began to reshape the planet itself. By releasing oxygen, slowly, invisibly, they started altering the atmosphere, bit by bit. But oxygen didn't just accumulate. At first, it reacted with iron in the oceans, forming banded iron formations. Stripes of red and gray rock you can still see today. These bands are geological signatures of the Earth taking its first deep breaths. Over time, oxygen would accumulate in the air. And for most life back then, that was terrifying news. But we'll get to that in the next chapter. Earth's surface gets an upgrade. During the Archean, Earth's crust was on the move. Remember, plate tectonics were already underway, but now, small land masses called cratons were beginning to stabilize. These became the building blocks of future continents. Cratons are ancient, incredibly tough slabs of rock, some over 3.5 billion years old. They're still with us today, hidden beneath modern continents. Think of them like the original tectonic bedrock that everything else built upon. And between these rising land masses, vast oceans teeming with microbial life. But no forests, no oxygen, no ozone layer to protect against UV radiation. Life was mostly underwater, and that's probably what saved it. Alien weather and an orange sky. Let's talk about the weird weather. With high levels of methane and no oxygen, the atmosphere was thick and hazy, possibly orange or brown, like Saturn's moon Titan. Clouds would form from sulfuric acid or even hydrocarbon smog dye. And lightning? Constant. Some scientists believe lightning in this volatile atmosphere may have helped create the first organic molecules long before. Even in the Archean, it continued to provide the raw energy life needed to push forward. But it also made Earth look nothing like it does now. Imagine a sky without blue, a sun dimmed by haze, storms you could see across the horizon, with thunder echoing across lifeless land. Alien, but ours. The faint young sun paradox. Here's something that still puzzles scientists. With the sun being 30% weaker, Earth should have been frozen solid during the Archean. And yet, it wasn't. Why? Greenhouse gases like methane and carbon dioxide likely built up in the atmosphere, trapping heat and preventing a global deep freeze. Microbial life may have even helped regulate this balance over time, inadvertently keeping the planet habitable. It's a strange idea. Microscopic life, too simple to even have a brain, accidentally stabilizing a planet's climate system. But hey, that's Earth for you. A planet where even the smallest forms of life can have world-changing effects. Archean Earth. A world in transition. By the end of the Archean, Earth was shifting. Oceans dominated, but bits of stable land were growing. Life was still microscopic, but it was laying the biochemical groundwork for everything to come. Cyanobacteria were now pumping oxygen into the seas at a steady pace. At first, this oxygen reacted with oceanic iron. But eventually, the oceans became saturated, and the oxygen began to leak into the atmosphere. And that would change everything. Because for life that didn't need oxygen, life that had thrived in its absence, this invisible gas was toxic. We were on the edge of the first mass extinction in Earth's history, and no one even knew it was coming. Coming up next. In the next chapter, we'll watch the atmosphere transform as oxygen becomes a deadly force. Microbial empires collapse. The oceans rust, bite, and Earth's biosphere enters a deadly evolutionary bottleneck. But from that chaos comes opportunity. It's the start of the greatest paradox in Earth's story. How death cleared the way for life as we know it. What if the very thing that gives you life was once one of the deadliest substances on Earth. Today, we take oxygen for granted. It fills our lungs, fuels our cells. Without it, we wouldn't last minutes. But for Earth's earliest life forms, those microscopic anaerobic survivors of the Archean world, oxygen wasn't a gift. It was poison. And as it crept silently into the atmosphere, it triggered one of the greatest biological catastrophes in Earth's history, the Great Oxidation Event. But this extinction didn't arrive with a bang. It was quiet, invisible. It took millions of years. And when it was over, the world would never be the same again. Oxygen. A biological betrayal. Let's rewind. By the end of the Archean eon, cyanobacteria had been around for hundreds of millions of years, performing a trick called photosynthesis. They took in sunlight, carbon dioxide and water, and released oxygen as a byproduct. At first, this oxygen had nowhere to go. It bound with iron in the oceans, forming rust, literally. This process created the beautiful red and silver rocks we now call banded iron formations, which are still mined today for their precious metals. But after enough time, the oceans ran out of free iron. So, where did the oxygen go? It began to rise into the atmosphere. And that's when the trouble started. The first silent killer. For anaerobic life, organisms that evolved in a completely oxygen-free world, the appearance of oxygen was catastrophic. It destroyed cellular machinery. It oxidized molecules. It tore apart the biochemistry of an entire biosphere that had never needed it before. There was no ozone layer yet, either. So the oxygen didn't just harm life, it also made it possible for sunlight to produce toxic forms of oxygen like hydrogen peroxide and superoxide, which are like molecular wrecking balls. Imagine a slow, invisible flood of poison creeping into your habitat. There's no escape, no adaptation, no time to evolve. Entire microbial ecosystems, hundreds of millions of years old, collapsed. We don't have fossils of these extinctions. No bones, no gravestones. Just the silence they left behind in the geological record. Atmosphere. Remixed. Let's talk about what this did to the atmosphere. Before the Great Oxidation, Earth's skies were thick with methane, a powerful greenhouse gas. It kept the planet warm, despite the faint young sun. But when oxygen started rising, it reacted with that methane and broke it down, turning it into carbon dioxide, a weaker greenhouse gas. This was a double punch. Oxygen killed anaerobic life. The breakdown of methane cooled the planet dramatically. And so, Earth entered a new phase. A planet with oxygen. And possibly its first global ice age. A true planetary reset. Snowball Earth prototype. We'll talk more about Snowball Earth in the next chapter, but here's the teaser. It's possible that the Great Oxidation Event helped kick off one of the first planet-wide freezes. With less methane and more coal, the climate cooled. Some models suggest that ice may have reached the equator. Imagine a frozen planet, glinting like a white marble in space, locked in a deep freeze for millions of years. And yet, life did survive. It clung to volcanic vents, to cracks in the ice, to underground aquifers. And even in this devastation, a new kind of organism began to rise. The rise of aerobic life. Not all microbes hated oxygen. A rare few had evolved to tolerate it, and even use it. These were the ancestors of aerobic life. Organisms that could breathe oxygen and generate energy more efficiently than ever before. Why is that important? Because aerobic respiration creates about 18 times more energy than anaerobic methods. That meant these oxygen lovers could grow faster, move more, and build more complex structures. It was a total evolutionary game changer. So while most of Earth's biosphere was collapsing, these oxygen-using microbes were quietly taking over. Their time was coming. Earth's first blue skies. Here's something poetic. As oxygen began to dominate the atmosphere, Earth's sky literally changed color. Before oxygen, the sky may have been hazy, reddish, or orange, filled with volcanic gases and methane. But as oxygen levels rose and the atmosphere stabilized, Rayleigh scattering, the same effect that makes today's sky blue, took over. The first blue skies appeared. Imagine that moment. An alien world with a brand new shade of sky. Light bouncing in a way it never had before. Shadows changing. Sunsets glowing differently. To us, it's normal. But for ancient Earth, it was a revolution. A change in color meant a change in chemistry and in possibility. The ozone layer's debut. There's one more unsung hero born from the Great Oxidation. Ozone. As oxygen built up in the upper atmosphere,